Here we're going to be looking at the electron configurations of cations. Typically the atoms that form cations are metals and transition metals, so we're going to be looking at elements near the lower left-hand corner of the periodic table. Transition metals are a little bit trickier, so we want to make sure to deal with metals and transition metals a little bit differently. The main group metals themselves typically remove electrons to get to a noble gas subshell that is contained underneath. Just like the electron configurations of anions, really why atoms are becoming charged is to get to a noble gas configuration. So we're doing it in this case by losing electrons. So here I ask for the electron configuration of sodium plus. As always, we want to start with the electron configuration of the neutral species. So when we look at a periodic table for sodium, we backtrack, we realize it has a neon noble gas core, and then we have added one 3s electron to it. So the electron configuration of sodium neutral is the neon noble gas core plus a 3s1 electron. So you can already see the noble gas core here. All we have to do is lose an electron. So when we go from sodium to sodium plus, we lose an electron. We lose this 3s1 electron, and really what we're left with is our neon noble gas core. If we were to expand the electron configuration of neon out a little bit, we would see that it is got a filled 2p subshell. So by having this noble gas core, we have gained stability because now all of the subshells inside of sodium plus are filled. So the same thing is true when we look at aluminum 3+. To look at the electron configuration of neutral aluminum, so aluminum's right here, backtrack, we have a neon noble gas core. We then add two 3s electrons, so we have 3s2 electrons here, and then we put one electron into the 3p subshell. In this case, to get to our neon noble gas core, we need to lose 3 electrons, and that's what we do when we go from aluminum to aluminum 3+, is we lose these 3 electrons, and what we're left with is the electron configuration equivalent to neon. So with titanium, I'm asking what's going to be the electron configuration of titanium 2+. We want to take a second and make sure we consider the electron configurations very carefully whenever we're dealing with transition metals, and that's because now we have d electrons involved, and that kind of complicates things. So here, this is a good example. We have titanium, we want to lose 2 electrons, and really the question is, do we lose the 4s2 electrons or do we lose the 3d2 electrons? And this is something that you need to remember, is that actually the 4s2 electrons are lower in energy because they have a higher n value than the 3d subshell. So what happens is actually the 4s electrons are easier to remove than the 3d electrons. So when we go to titanium 2+, we lose the 4s electrons. And so the electron configuration of titanium 2+ is argon plus 3d2 electrons. So this is something that you just need to remember, is that the 4s electrons are lost first. You will see some textbooks that actually have you write the electron configuration with these two reversed, which is okay. You will see textbooks that have it both ways, but you just need to remember that the 4s electrons tend to leave before the 3d electrons. And you're going to find out, because our transition metals here, you're going to find that many transition metals have a +2 state. So this is also where we can understand why certain transition metals have more than one oxidation state. So that's something that was special with transition metals. They could have more than one charge, and it's in these electron configurations where we can see why this is possible. So if we look, we want to write the electron configuration of Fe2+ and Fe3+. Once again, we start off with the electron configuration of neutral ion. So we backtrack, argon core, 2 4s electrons, and then 1, 2, 3, 4, 5, 6 3d electrons. So this is the electron configuration of it in its neutral species. So to go from Fe neutral to Fe2 plus, the first thing to be removed is the 4s electrons. So Fe2 plus has an electron configuration of argon 3d6. And then now to go from Fe2 plus to Fe3 plus, we remove one more electron. So here it comes out of the 3d subshell, so we go from 3d6 to 3d5. And one of the things that we had discussed earlier is that half-filled d subshells are relatively stable. So in this case, half-filled d subshell is 5 electrons. So losing an extra electron going from Fe2 plus to Fe3 plus is relatively easy. We actually gain some stability by having this half-filled subshell. So here you can see that it's relatively easy for iron to be +2 or +3. And this is part of the reason why transition metals have more than one charge, or the possibility of more than one charge, is because they have d electrons involved. Let's look at one more. I asked for the electron configuration of copper 1 plus and copper 2 plus. Once again, we want to start with the electron configuration of neutral copper. We backtrack, we have an argon noble gas core, we have 2 4s electrons, but here when we count it out we have 9 3d electrons, and that's one of the numbers that we make sure that we pay attention to, is that to gain stability, in actuality the d electrons will grab onto an s electron to fill its subshell. So the electron configuration for neutral copper is actually argon 4s1 3d10. So instead of being 3d9, the d electrons grab an s electron to get to the full subshell. So you need to make sure that you have the correct electron configuration of your neutral species to make sure that you get the correct electron configuration of your cations. So here, to go from copper to copper plus, still it's the 4s electron that leaves first. So we lose that. For copper plus, the electron configuration is argon 3d10. Then now we remove one more electron to go to copper 2 plus. Really the only place that electron can come from is from the 3d10. So the electron configuration of copper 2 plus is argon 3d9. One of the things you should realize is here we're breaking the filled subshell of the 3d, and this is a general consideration that full and half-filled subshells are stable, but it doesn't mean that we have to have them. So it is possible to make copper 2 plus. It is possible to remove an electron to break the full 3d subshell to get to 3d9. But one of the things that we know is copper 2 plus is relatively unstable. It would like very much so to grab onto an electron to go back to 3d10. As somebody that has used copper 2 plus, we can say that it is very unstable and it needs to be treated with a certain amount of care, because it would really like to grab onto an electron to become 3d10. So it is possible to have copper 2 plus, but we can understand that it is fairly unstable.